So we left off when we were graphing. So this one does have an issue with the domain. So the ones that are just polynomials, it was negative infinity to infinity. So in this case, we have x can't be 2 and it can't be negative 2. So you can write that however you want to. You can write it in interval notation, which is a little bit more complicated, or you can just say x isn't 2 and x isn't negative 2, right? That's fine. Or x is not plus or minus 2. So the vertical asymptotes then are x equals 2 and x equals negative 2. The first derivative, so we do our low d high minus high d low. So check yours. All over the square of what's below. And we've been talking about that little trick where you can pull out common factors. So in this case, we actually have a common factor of 2x. So you could pull a 2x to the front if you want to. Although this one's not too hard to multiply out. So we get this all over the thing squared. So I think we should have negative 8x over x squared minus 4 squared. Did you guys get that? Okay, so that means we have 3 critical values. So we have x equals 0 and we have x equals plus or minus 2. Okay, so we're going to put this number line, but we know that the AP test doesn't actually grade this number line. So if we were talking about where things were increasing, decreasing, where there's a maximum, we need to write out why that was happening. Like f prime is greater than 0 on this interval, f prime is less than 0, right? So as we do this in f prime, if I plug in 3, I usually look at the most simplified form. You guys see how the bottom is always positive, x squared minus 4, and then the quantity squared? When something's squared, it's always positive. So we can kind of just ignore the denominator as we're plugging things in. So if I plug in 3, I get negative 8 times 3, which is negative. And then if I try 1, I get negative 8 times 1, which is negative. And then the other two are positive. So it's positive, positive, negative, negative. Which means that f goes up, up, down, down, like that. So then our second derivative is going to be, again, low d high minus high d low. And so the d low part involves the chain rule. So we're going to do 2 times x squared minus 4 to the first, and then times 2x, all over the square of what's below. So it's now going to be raised to the fourth. So x squared minus 4 to the fourth. Did you guys have that for your second derivative, or did you not get there yet? So we're going to look for those GCFs. So we have a GCF of one of the x squared minus 4s, one of the negative 8s, and I think that's it, right? So we're going to pull x squared minus 4 and a negative 8 out all the way in the front of a big bracket. Make sense? So we're going to look for anything that's left. So we have, in the first spot, we have an additional x squared minus 4. Right? We lost the negative 8, and then we had minus, and now we have an x, a 2, and a 2x. So I'm going to have, what, 4x squared, and then nothing else, right? So you can see how I got that. So we have the x from here, the 2, and the 2x. And then we still have the thing to the fourth. So as we reduce out, we see that we have an x squared minus 4 here, and we can get rid of the 1 there. Yeah? I think there's an additional x right here, right? So x, 2, and 2x. We just pulled out the negative 8, but we still have the x that's attached to it. Does that make sense? So we end up having negative 8 times negative 3x squared minus 4 all over x squared minus 4. So you could pull out the negative even, and you could have positive 8 times 3x squared plus 4. Sorry, there's a 3 there. Over x squared minus 4 cubed. And you can kind of tell from the numerator, you're not going to get any additional critical values because we have a squared plus something, right? If you set that equal to 0 and tried to solve, do you guys see how you would get I solutions? Okay, we don't have I's in Calc 1, so we're not going to worry about it. All right, so then we do have our critical value, or our points of interest, right, of 2 and -2. And why are those points of interest? Because those are asymptotes. We need those on every single derivative. So both first derivative and second derivative. Okay, so we start sketching things out. Well, I guess I asked more questions. So horizontal asymptote. So what do you guys have for the horizontal asymptote? Do you guys see how you have, looking at your largest degree, so we had x squared over x squared minus 4. Our largest degree is x squared. So x squared over x squared is 1, right? So our horizontal asymptote is y equals 1. Our intercepts, so if I look at my x squared over x squared minus 4, and if I wanted to find an x-intercept, I plug in 0 for y. So I have 0 equals x squared over x squared minus 4. Do you see how the denominator of that doesn't matter? If I have a fraction equaling 0, it's only coming from the numerator. So x equals 0 is our x-intercept. That means y equals 0 is also an intercept. It's at 0, 0. But if I plug in 0 for x, you guys can see that, because you'd get 0 squared over 0 squared minus 4, which is also 0. Okay, and then vertical, oops, did I not have that one? Vertical asymptotes? No, we did those already. Okay, so putting it all together into a giant graph. So we have our vertical asymptotes at 2 and -2. We have our horizontal asymptote at 1. We had our x and y intercept at the point 0, 0. We saw that it was increasing, increasing, decreasing, decreasing. And for our second derivative, I didn't put those on there yet, did I? We again had vertical asymptotes. And I like to draw that. Maybe I should draw that here too on my first derivative. Okay, and then if I check for my concavity, my numerator is always positive with this 8 times 3x squared plus 4. No matter what I'm plugging in, I'm going to square that. So 3x squared, right? So it's positive on top. But then what about the bottom? The bottom's cubed, right? So I'm considering what happens when I plug into the cube. So if I have like a -3 and I square it, and then -4, and then I cube it, are you with me? So if I plug in like something over here, like -3, the top is always positive no matter what. But the bottom, if I have -3 and I square it, I get 9 minus 4 is 5, and then 5 cubed is 125. It's positive. Does that make sense? Okay, do you guys see it will be the same for +3? And then 0 will end up being negative, because we'll have 0 minus 4, which is -4, and then cubed. So that means that we have concave up, concave down, concave up. So like on your test, like I was saying, I'm not going to ask you to graph everything. I will on like a little quiz. But it takes a lot of time to graph everything. I don't want to spend your whole test graphing. But I might ask, where is it concave up, where is it concave down, and so on. Okay? All right, so, yeah. Uh-huh. Where's what? So horizontal asymptotes are what we have when we do like limit as x goes to infinity. So there's a shortcut we learned. We talk about like whether it's top heavy or bottom heavy. Yeah, it's just the original equation, yeah. Okay, I see what you're asking, yeah. Okay, so we want to be increasing and concave up for the first one. So the only way we can draw that is here. Do you guys get that? Okay, and then in the middle we want to be concave down, and we want to go increasing and then decreasing. Do you guys see right here when you have something that's increasing, tapers off to a slope of 0, and then is decreasing? That has to be a maximum, right? So we're going to have a maximum at that point 0, 0, which we already had. Right? If we didn't have the y value with 0, we would plug into the original to find it. And then the next part is concave up, but now it's decreasing. So think about how to draw something that's concave up but decreasing. Right? It's going to look like this, right? So that's our graph. Other things that you can, use for graphing, this is an even function. Do you guys remember what it means to be even or odd? right? If I plug in 2 and negative, well, not 2 because those are asymptotes, but if I plug in like 3 and negative 3, I get the same value because these are both squared here. X squared over x squared, right? Does that make sense? So it should be symmetric. Like both sides should look exactly the same if I like fold it over on itself. Okay, make sense? All right, so the last one we're going to talk about is using a graphing calculator if allowed. So let's maybe look at this one instead. Okay, so on this first, so I'm going to do the second example. So h of x equals x raised to the sine of x. Okay, if this was on the calculator section and it was asking where it's increasing, decreasing, concavity, or whatever, there's actually a way that you can graph a derivative on your calculator. Okay, so what we're going to do is we're going to put this in for y1. So we're going to put x raised to the sine of x, like that in our calculator. You probably don't need the parentheses around sine of x, but and we can graph it and we can kind of see what it looks like. So we know how to find maximums and minimums on a calculator, right? We just find, we do second trace intersect. So I could find this maximum here, this minimum here, this maximum here. Do you guys see the graph? So it looks something like, and I didn't really tell you what interval it's on. Let's make it go out to 20 and see what happens. Okay, so it's getting bigger and bigger and bigger. I probably should have given you an interval. So let's say on negative 10 to 10. Because I don't want to find all of them. So let's put our window negative 10 to 10. So you can do zoom standard, so zoom 6, or you can just put it in negative 10 to 10. Okay, and that's what our graph looks like. So it goes up again, right, and then it comes down. Do you guys all have that? So something like that. Yeah? Okay. So if I want to find those values, I can find maximums and minimums, right? I could find all of those on my calculator. Right, I would do second trace and then I do maximum. So I can do second trace, and if I wanted to find that first maximum, I arrow over along the curve. I get on the left side of it, hit enter, get on the right side of it. Is this all familiar? But our issue is that we don't know how to find points of inflection. Okay, and you can kind of estimate where points of inflection are. Like people will be like, oh, it looks like it's going to be like here, and somewhere around here, and somewhere around here, and somewhere around here. Do you guys see those where it's changing in concavity? Sometimes that's hard for you guys to recognize. See how that's concave up, concave up, concave up. And the other parts are concave down, concave down. Do you guys understand what I'm saying? Okay, so we're finding those places where they switch. But how can we possibly find that on our calculator, right? Okay, so here's what we're going to do. So we have that in for y1. I want you to put something in for y2. Do you guys remember that button that we did that was nderiv, and it found our derivative at a certain x value? Okay, we're going to do nderiv, and we're going to take the derivative of a y1 at every single x value that we're graphing, which seems weird. But it's going to look like nderiv y1 x comma x. So previously we put a number here. Now we're just going to put a generic x. And your calculator might pull it up as ddx y1, and then we'll say x equals, and you want to put x equals x. Okay? So are you guys like, how do I put y1 in? So we're going to go to y, to the y equals. Of course I have my, there we go, okay. And then under y2, we want to put that derivative thing. Can you guys see this at all? It's so hard to see with green. Okay, so I'm going to do nderiv, so I'm going to do math 8. And mine pulled up the word nderiv. Yours may not look like that. It may say d over dx, right? And then I want to take the derivative of whatever I put in y1 Okay, so a handy trick that we'll use a lot throughout the year is we're going to pull y1 and put it in this spot. So I'm going to hit the button that says vars. So everybody hit vars, variables. Y vars, function, y1. Now okay, so it says n deriv y1, and we want to take it at every x value. So we do a comma, x, so that means take the derivative with respect to x, and then comma at every x value, so x. And you can end the parenthesis if you want to. And now what happens is if I hit enter, it's going to graph both y1, the original, and its derivative. So if I only want to see its derivative, then I can hit enter, or then I can go on top of the equal sign at y1 equals, hit enter, so I deselect it, and then I hit graph. So this is only going to graph the derivative. So this is graphing like f prime, right? It's right in there. So it's the slopes of all of this that we had before. Does this make sense? Okay, I could do that again and graph the second derivative as well. What would I do in y3? I would do n deriv of y2, right? X comma x, right? Does this make sense? So you could do all those. But if you think about it, I have enough information to find a point of inflection, even on that first derivative. How do I find like a point of inflection if I have f prime? Kind of weird. It's where the slopes are equal to 0, right? And where are our slopes equal to 0 on this graph? Make this bigger. Oh, jeez. Select. Okay, so this is the graph of y prime. If I want to find where y double prime is equal to 0, the points of interest, I go here and I find all the maximums and minimums, right? And we know how to do that on our calculator. Does this make sense? Do you guys get it? Okay. So I just wanted to show you guys how you